Okay, let's start it with lecture 8, part 2. We are going to talk about the speed of EF and partial differentiation and a lot more details. Okay. All right. So to look at the more detailed, description of what the partial derivatives are, etc., we'll take a look at this solid example of two-link manipulator. We already know the equation for that two-link manipulator, and we'll use that particular equation. Last time we used a general equation, but this time we'll use the solid equation, which we have already derived a long time ago. All right, so let's start computing. Partial derivatives, all right. So first one here, let's look at this x2 and partially differentiate in terms of theta 1. Okay, so this there theta 1 and theta 1 here. And according to the linearity here, that's a very, very, very handy tool. Linearity, I can break that into two parts and take a look at this first one here and the second one separately. Okay. Now, here, this theta 1 only, so therefore, partial derivative changed to the regular derivative, which is easy to do it. And then, the other side, since when you take the partial derivative, all other variables becomes just a constant. So here, theta 1 plus theta 2 here, but theta 2 is just a constant. So this is a function of theta 1 only. Therefore, this again becomes d theta 1, the regular differentiation. Okay, then we can use the formulas and so forth. We already know that's cosine differentiated cosine, or sine differentiated cosine. Or theta 2 is just a constant, so therefore doesn't change anything. All right, so we can do the same thing for delta f the partial derivative of x2 in terms of theta 2. Okay, linearity again, theta 1 is just a constant. This is exactly the same thing. Here, theta 1 is just a constant. So if you differentiate in terms of theta 2, this is just a constant. So therefore that's 0. 0 drops. Great. So you don't have to worry about that part anymore. This part here becomes cosine. All right. How about the other one? y2 differentiated by theta 1 partially. Exactly the same thing we do. Linearity, change theta to d and perform the regular differentiation. Okay, final one. Delta g over delta theta 2, pretty much the same thing. Theta 1 drops out, and that's all we have. So if we put everything together, that's Jacobi matrix here becomes this one here. Okay, so therefore you can compute the Jacobian, which is the determinant of this matrix here. Well, you multiply these two together, subtract the product of those two. Well, lots of terms, but if you multiply them out and see what's going on, then you can see that you can, here, this one and that one, that one, that one. Well, if you look at this one here, 2 squared is squared cosine, sine, cosine, sine. So these two terms will drop, right? These two terms will drop. So that's the only time we have. And here, L1, L2 this is L1, L2. So therefore, what we got is this. Aha. Let me erase this thing here. So we have cosine times sine, that's minus sine. So I should start from here. Cosine times sine minus cosine sine. And theta is reversed. So therefore, we can use addition identity, right? So if I write this one down in this form, I guess you can remember. If you cannot remember, okay, let's look at the list of those identities. So we can combine these two together, becomes sine theta 1 minus this one here. Wow. Wow, it's right. Look at this. Oop. I better be able to write down this theta 1, theta 1. Theta 1 drops. So that's all you got. This is a Jacobian. This is a Jacobian. So therefore, singularity, namely determinant Jacobian is equal to 0, depends only on theta 2. Theta 1 doesn't matter. That's interesting, don't you think? Okay. So this singularity determinant of J, Jacobian is equal to 0, meaning that the sine theta 2 is equal to 0. Therefore, theta 2 is equal to 0 or plus minus pi or whatever the add and subtract 2 pi's. So let's take a look at this one here. So we got this for the singularity. At the singularity, what's happening here? All right? Theta 2 is equal to 0, meaning theta 2 is measured from this direction, right? Direction of link 1. So theta 2 is equal to 0 means link 1 and link 2 are on the same direction. Excuse me. And theta 2 is equal to pi, meaning that this is link 1 direction, and this way is pi. Oop. And this way is negative pi. Because if you remember, theta 2 was measured this way, right? So this is plus direction for theta 2 and the other pi. But anyway, what's going on is totally folded, right? Well, I'm not sure whether you actually can do this or not. But mathematically speaking, this or that is happening. All right. Links are totally expanded or completely fold. All right. So let's take a look at theta 2 is equal to 0, totally extended. That is easier to conceive because totally folded, probably mechanical difficulty there. So let's look at that one. Okay, and theta 1 is free. Okay, let's put theta 1 is equal to pi over 2, meaning pi over 2. That means that the entire link is on the x-axis. This is x-axis. This is y-axis. Okay, so this is what's going on. So what's going to happen? Theta 2 is equal to 0 and theta 1 is equal to pi over half. Then, if you put those values into those cosines and sines, cosine theta 1 and cosine theta 1 plus theta 2, both of them become 0. And then sine theta 1 is equal to 1, sine theta 1 plus theta 2 is equal to 1. Yeah, theta 1. Pi over half. So that's 1, 0, 0, 1. So that means the Jacobi matrix becomes, this Jacobi matrix becomes this. Whoop. Let me get rid of this y. Okay. The first row becomes 0. The second row becomes this. Simple, very simple one. But those zeros, that could give us some trouble. And that is very true. So if you multiply that Jacobi matrix to theta 1 dot, theta 2 dot, what's going to happen is that 0. x2 dot is equal to 0. y2 dot is equal to this one here. Okay, y2 dot is y directional. This is y directional speed, and x2 dot is x direction. So x directional speed is equal to 0, regardless of the speed x theta 1 dot and theta 2 dot. So regardless of how you move those two joints, x2 dot is equal to 0. You cannot move the end effector along the x-axis. Well, that's true, right? This is totally extended. So the only way it can go is up or down. Cannot go this way. Okay, that's what this singularity says. So when the singularity happens, there is a limit as to how things can move. Oh, by the way, here I used one word which you may not be familiar with, ulog. This is actually my favorite word, ulog. And that means ulog without loss of generality. And I've been repeating myself again and again. Mathematicians are lazy, so therefore, instead of writing all of those, we just say ulog. Okay, so it's not a logarithm, okay, it's a ulog. All right, anyway, okay, so we know what the Jacobi matrix is and what Jacobian is, what the singularity is, blah, blah, blah. So that's pretty much the end of what we need to do it. But let's revisit that speed of EF here, revisit. The reason for that is that we can compute theta 2 dot, y2 dot from theta 1 dot, theta 2 dot directly. Using the list and the rules of differentiation, we can compute those directly without going through the computation of partial differentiations. Okay, let's get started from the same point here. And then consider x2 first. So x2 dot is the differentiation of this one in terms of t. Right, speed, okay? In terms of t. Time differentiation. So if you want to do that, of course, theta 1, theta 2, those are functions of time, okay? Those are functions of time, like theta 1 of t and theta 2 of t. So what we can do is, well, first linearity. I always forget about this one here. Linearity is so, how should I say, trivial. So clearly true that I forget to tell you that this is linearity, and you break down that, and then you use chain rule. Wow, we know the chain rule. So this is theta 1 in terms of differentiation of sine theta 1 in terms of dt. So differentiation of sine theta 1 in terms of theta 1 and then theta 1 dt. Chain rule. Exactly the same thing except that you set this to be that. Then this is what you got. All right. So let's compute that. All right. The first one becomes sine. I mean, differentiation of sine becomes cosine. This one here, of course, becomes cosine. And d phi over dt here is theta 1 plus theta 2, and both of them are time functions. So actually I use the linearity again here so that you can have theta 1 dot plus theta 2 dot. So from here to there is linearity. Linearity is useful. So if I put theta 1 dot together and theta 2 dot, then this is what you got. And if you substitute the phi, what phi was, then this is what you got. Well, of course, this is the same result as we have gotten. And similarly for y2. I love this similarly for, because pretty much you can do the same thing. And what the teachers do normally of this one here is that to make this as a homework for you to actually get this one here. Well, only thing you have to do is to follow exactly the same thing, so not much of difficulty there anyway. So we got those two in matrix format. This is what we got. That's exactly the same as the one we got before. All right. So So that means that even if you're talking about the partial derivatives and so forth and the speed and so forth, there are a lot of things that we can do using the differentiation table and the rules. Okay. Coffee break here is importance of Jacobian. We've been talking about Jacobian, Jacobi matrix quite a bit. And there is a reason for that. Because Jacobian is so important. So important. Manipulation, the manipulator control method. Well, if you look at the modern day manipulator control, there are several methods. The first one, the simplest one, is called PTP, point-to-point control. So you only care about where it starts and where it ends. You don't care how it goes. Only the end points. Okay? The next one is CP, continuous path, meaning that you care how not only the starting and end point, but also the trajectory. Okay? You want to control how the transfer from one point to the other happens. And even more, velocity control. Not just the trajectory, but the speed as to how fast or how slowly it moves. You want to control that. So point-to-point is the simplest, then continuous path, and then velocity control. So velocity control is a lot more sophisticated control, and which is what we need, what we use, current control standard. Like if you look at the painting, okay, you want to control the trajectory, but also you want to control the speed, right? So that's why. All right. We cannot do this without Jacobian, right? We have computed the speed of the end-effector in terms of the speed of the joints. So Jacobian is crucially important for modern day control. Lots and lots of studies on how to compute the inverse Jacobi matrix. Why? Because this is the one will tell you the joint speed in terms of the speed of the end-effector. So end-effector, you want an end-effector to move at certain speed. So that is given. Okay? The end-effector speed is given. Now, from that, you want to compute the speeds of joints. That's why you need this one here. So that's why there are lots of studies on how to compute this one. It is a very complicated thing to do it. All right. The next thing I'm going to talk about here is position of end-effector of two link. Again, why? We have done this already long time ago, and I have used that equation, right, in computing the speed of the end-effector in terms of the speed of the joints. But this again, meaning that now we will start talking about the practical situation. We do have tools to do this now. So here, what I would like to do is to show you how we can use the tools, differentiation, partial differentiation, those to do the very practical thing, which is the adjustments. Well, question is specifying theta 1, theta 2 end-effector at the target position. Ideally speaking, yes. Mathematically speaking, yes. Of course. But answer, in general, no. In practical situations, no. You specify theta 1, theta 2, and this one here is not exactly at the position where you want it. Okay, why? Well, I guess everybody knows why. The reason for that is that practical parts are not ideal. For example, backlash. Are you familiar with the backlash of the gears? Let me show you the diagram here. Well, two gears are moving like this one here. And there got to be a small gap between two gears. Otherwise, they won't move. If there's no gap, then gears won't rotate. Gears won't move, right? there has to be a gap. And this gap is called the backlash. So each and every gear has to have backlash. Some cheap gears do have a lot of backlashes, and expensive ones, more sophisticated ones, has small backlash. But backlash has to be there. So what's going to happen? If backlash is there, okay, depending on which way moving, there is, well, let me exaggerate. There is an error. This one and that one, the position is different, right? So that's going to happen. So in a practical situation where you are actually moving the robot and try to let your robot to grab something like that, you have to do the fine adjustment, fine, not the big adjustment, fine, small adjustment. That's why I put delta here. Fine, small adjustments. So how? The question is, how? Okay. The first thing is this. You have to be able to find out how much this one here. But first thing you have to do is to do this. This is the position you want your end-effector to be. But this is the actual position. So you should be able to measure the difference. In other words, you have to measure the error of the position, of actual position and target position. For that, you need to use like camera or some other form of measuring device, sensors. So you use sensors to measure the error in the end-effector position, and then you wanna find out this one here. Okay, so this is something you measure. Sensor. Sensors, should I say? From sensors, you get this one here. And this is something you want to find out. For that, what you need is to have a relationship which can tell us how these two are related to each other. By the way, I put the delta here and the position error of the end-effector, and hoping that the position error is small, okay? If there's a large position error, then you just move it, okay? So, what is the relationship between these two? Let's find out. Okay. Delta x2, by definition, is from theta 1 to theta 1 plus delta theta 1, theta 2 to theta 2 plus delta theta 2, and the difference between these two. That is the definition of delta x2. So let's compute this one here. Remember that we did do nothing trick of mathematics, and I subtracted and added the same thing, so that's adding 0 and multiply and divide, so that's multiplying 1, do nothing. And this equation we already know. We already used this equation. And this one was called 1, and this one was called 2. So average rates of changes with respect to theta 1 and theta 2, respectively. This is in terms of theta 1, theta, and this one for with respect to theta 2. Okay? So this is pretty much a relationship between delta x2 and delta theta 1, delta theta 2. So if we do know those two, then we can write down an equation. Not so quick. Okay? Those cannot be computed before start moving. Why? Because this is from theta 1 to theta 1 plus delta theta 1 and dividing by delta theta 1. Meaning this is an average speed, don't you think? Okay, those are average, well, speed is not a good word probably. Average ratio. Here, this is average ratio. And we don't know how much that the difference is going to be. So what is the engineering solution for that? Okay, instead of that, we use something which we can compute, meaning that replace them with instantaneous rate of changes computed at the start. When you start fine adjustment, you can compute those values. How? You let delta theta 1 and delta theta 2 goes to 0. Well, of course, when they goes to 0, it goes to the starting position, right? Okay? So, that's what we do. But only in here. Okay? Don't let this theta 2 and theta 1 go to 0. Only for those coefficients. And if we do that, this is nothing but the partial derivative of f in terms of theta 1. And this is partial derivative f in terms of theta 2. Wow, very simple. So this delta x2, the error, I mean small move, small variation in the x direction of the end-effector is related to small variation in joint 1 and joint 2 in terms of partial derivatives. So this is a relationship we can use. So for similarly, we can do that, and of course we did this many times. So this one is equal to J times that. Jacobi matrix again. So fine adjustments, once again, Jacobi matrix. So if you measure this one here, you can multiply J inverse to it to compute delta theta 1 and delta theta 2, so you know how much you have to move. Wow. So let me repeat myself. Jacobi matrix Jacobians are very important to find the speed of the end-effector, but that's not all. Jacobi matrix and Jacobians are very important to do the fine adjustment of the position of end-effector. And Jacobi matrices are indispensable. The Jacobi matrix and Jacobians are indispensable for that as well. Okay. Oh, this is coffee break, but I'd like to tell you the actual industrial robots, how they go. You remember? Probably you not remember, but have you seen industrial robots moving very quickly to the vicinity near the target position and then move slowly to the target position? That's exactly what we do. We set theta 1, theta 2 and move, but there's got to be some error, so you do the fine adjustment slowly. That's what it does. So if you take a look at the industrial robot manipulator control, the motion from a start point and end point PDP. So this is PDP. You don't care, okay? And accelerate, constant speed, decelerate sequence. That's something we have already done. Use CP if necessary. If there is something in between, so you want to control the trajectory as well, use CP. Measuring position and direction errors. Cameras, whatever. And then compute the inverse Jacobi matrix there and compute the joint angle adjustment, this one here, using that and that, right? Those two. And do adjustment. And that's it? No. You did fine adjustment, but you still may have some error because of the non-ideal characteristics of the actual mechanism. So repeat 2 to 5 if necessary. So the looping this one here until you get small enough error. If this becomes small enough, then you stop there. So that's how we do the manipulator control in modern days. Okay? So Jacobians are important, and we do use Jacobi Jacobi matrix all the time. Okay, so, nope, sorry. The inverse Jacobi matrix, of course. So that's the end of this lecture here, and we will move on to the applications of the differentiations next time. Thank you.